Hello everybody, in this video we're going to be going over part 2 of nim. Now in the past episode we looked at an example of nim with only one pile. And it was an example where you had to take 1 through 3 from each pile, and the person who takes the last object loses. Now, today we're going to be going over different cases and just taking a look in general at nim games with more piles. So we're going to start with an example with 3 piles. And we're going to use this example to help us generalize how this version of nim works. So this game has 7 objects in the first pile, 5 objects in the second pile, and 3 objects in the last pile. Now, as we saw before, when we had one pile, for example, if we had 8 in a pile, the person who goes first wins. And that's because when you simplify 8 mod 4, it becomes 0. So the person who's at 0 in a position wins, technically, because the other person is forced to take something to make it 0. Now let's go back to our example right now. Now we saw that the magic number for one pile was 4, because when we had a pile with n objects, then when we put that mod 4, it would become something like, if it was 0, then the person who went first automatically won, and if it was anywhere from 1 to 3, then the person who went second automatically won. And this was because because 4 is a number that can always be achieved in 2 turns. And similarly, when we're playing with 3 piles, we have the same magic number 4. It turns out that when you simplify each of these piles, mod 4, the piles are essentially equivalent. So this group of piles is actually the same as this group of piles. However, we don't actually know how to simplify, as of now, we don't actually know how to simplify 7, 5, and 3 to 3, 1, and 3. Because we just know that 4 is a magic number. And we'll go over on how to do this. But first, we want to find some losing positions. Now, losing positions, like I said before in the last video, are positions where you automatically lose if you're in that position. And an example of a losing position in this game of 3 piles is 3, 1, and 2. And it turns out that 3, 1, and 3 is only just 1 above the 2 right here. So, since 3, 1, 2, which is a losing position, can be reached from 3, 1, 3, then the person who's at this position of 3, 1, 3 right now can just take 1 from the pile of 3 right here, and they will automatically win, assuming that they play knowing every rule, all the rules. So how can we just assume that a pile of 3 can be just simplified mod 4 to become something basically equivalent to the pile that was just simplified? So let's take a look at a game, but we're gonna write on the side what these piles are in mod 4. So as of now, it's 3, 1, 3. And let's say that our first player will go first and player 2 will go second. So first, player 1, knowing that 3, 1, 2 is a losing position, they will force the other player into a losing position, which is this, or 3, 1, 2 in the mod 4 form. Now let's take a look at what happens when player 2 makes their turn. So obviously we're going to try to break this up into cases. So what happens when they take from these unsimplified numbers, meaning numbers that are not really actually equal to their mod counterparts, but are still equivalent to their mod counterparts in mod, of course. So these numbers, we'll just consider them as unsimplified because they're not actually equivalent to their mod counterparts. So what happens if they take from any of these? Well, then naturally we want to simplify the 7 or the 5 into the 3 or the 1, because when we do that, then we'll get even closer to being at our base losing position. So obviously we remember that 4 is the magic number. So for player 1, it's guaranteed that for whatever 2 takes from 7 or 5, player 1 will always be able to simplify it to 3 or 1, depending on which one player 2 took from. So let's say for example, let's say that player 2 takes 1 from 7, then this would become 6, 5, 2, and player 1 would simplify it to 3, 5, 2. Notice that player 1 can always simplify it to 3 whenever player 2 takes from the pile of 7 objects. Similarly, with a similar logic, whenever player 2 takes from 5, we can see that player 1 will always be able to simplify it to 1. Now, if 7 and 5 were 11 and 9, this is still equivalent to what we had before in the mod addition. So what we'll see is that whenever the player takes from any of one of these, then we'll just simplify it to 7 and 5, and then whenever they take from any of these again, then it becomes the 3 and the 1 that we wanted before. So you can see that this method is foolproof whenever we have unsimplified piles. So this kind of proves why they're equivalent. But then you might be wondering, what about this 2 here that's unsimplified? What happens when they take from an unsimplified number? And this is where some logic is required when player 1 wants to win. So let's say that player 2 decides to take from this pile because they think that player 1 does not have a plan, since they already know that player 1 is just going to simplify the 5 or the 7. So they're taking from the 2 this time. Let's say they take 1 from the 2. Then we have 7, 5, and 1. And the simplified version is 3, 1, and 1. Now, how is player 1 going to deal with this situation? Well, player 1 will look at this simplified version, and they're just going to use logic. How can we make this into this thing right here into a losing position? And obviously, since 3, 1, 2 is a losing position, we are guaranteed to be able to make 3, 1, 1 into a losing position. So 3, 1, 1 can actually be transformed into 1, 1, 1 by taking 2 from the 3. So in its unsimplified form, this is 1, 1, 1 would be equivalent to taking 2 from the 7. So we have 5, 5, and 1. Now what, you may be asking? Well, now we're into a different base losing position. As you can see, we have 5, 5, and 1 now. But it's still the same, because we see that 5 and 5 are both unsimplified numbers. They haven't been simplified yet. So we're just going to do the same algorithm over and over. If they take from any of the unsimplified numbers, then player 1 can just simplify. Now, if they take from the 1, then you're just going to use logic in mod 4 to determine what to take in the next turn. So let's just continue this example. Let's say they take from the 1, player 2 takes from the 1, so we're at 5, 5, and 0, and this is equivalent to 1, 1, 0. Now, as you can see by logic, since we're trying to force player 1 into taking the last, we're trying to force player 2 into taking the last object, we can take from any one of these. It doesn't matter. So we're just going to take 1 from the first one, so we have 4, 5, and 0, which is equivalent to 0, 1, and 0. And you can see how we've already won by looking at this mod 4 position right here, simplified version. So we can just continue by our logic. If player 1, since both of these are unsimplified numbers, we're just first going to have to simplify them. So player 2 has to take something. Whatever they take, it will become, for example, if they take something from 4, it's blank, 5, and 0. But whatever they take, we realize that we know that player 2 can always simplify it to 4 minus 4 or 0. So in this case, this will go to 0, 5, 0 or 0, 1, 0 still. And when they take from the 5, they can take anything from the 5, but they can never get us to lose. Player 2 can never get us to lose. So whatever player 2 takes, doesn't matter. We can then simplify it to 0, 1, 0, and we have 1. So we can see that this algorithm is particularly useful for the version of NIM where you take anywhere from 1 to 3 objects from a pile. So now it's time to generalize. What about 1 to n? What if we're taking anywhere from 1 to n objects from a pile each turn? Well, think about it. When we thought about it before, we found that 3 plus 1, or 4, was the magic number, since 4 could only be reached in 2 terms. Similarly, when we're playing in this generic version, we see that n plus 1 is the special number. So all we're going to have to do is work in n plus 1, mod n plus 1, looking at the piles in mod n plus 1 always. So, of course, this method requires that you know a losing position. That is a position that you know is guaranteed to make the other player lose. And in the example of 7, 5, and 3, we found that 3, 1, and 2 was a really good losing position that we could automatically get to on our first turn. Similarly, we can do that with a game like this and win. But we're not done yet. Remember in the last episode of NIM, the first episode of NIM, I talked about a version of NIM where the person who takes the last object actually wins. And it turns out that you can find a similar algorithm that is really similar to the one we just talked about that works for this version of NIM. And all you're doing is just finding a base losing position, unsimplifying it using whatever it was, maybe mod n plus 1, finding the magic number, I guess. And once you unsimplify it, you can find a certain losing position when unsimplified is just one move away from the starting position. Now, of course, there are some cases where you have to go second to win. And of course, those examples are pretty obvious. If the initial position is a losing position, for example, 5, 4, 0, there's nothing you can really do because you're already in a losing position. Now, 5, 4, 0, when simplified in mod 4, so if we're playing the version where you can only take 1 to 3, simplifies to 1, 0, 0 in mod 4, the simplified version. So obviously, you can see that you've already lost. But of course, that all depends on who's playing, because the person you're playing might not know any of these algorithms. So the next time you want to play NIM with somebody, you'll have a better chance of winning with these new algorithms. Thanks for watching. I hope you enjoyed this video of NIM Part 2. If you haven't checked out nim part 1, you should have checked that out a while ago because I did reference it in many parts of this video. So thanks for watching. I hope you enjoyed.